Let's use Simpson's rule to affect the approximation of the natural log of 2. With the last video that we did, we found that for an error less than 1 over 10,000, that we could use n equal to 8, just remembering that for the Simpson rule, n must be even. That is, the number of subdivisions must be an even number. And so we figured out that if 8 will work, that will give us a subdivision length of 1 divided by 8, since the interval length in this particular problem is 1. So as we did before, we get this partition 1, 1 plus 1/8, 9/8, 10/8, 11/8, etc., 14 over 8, 15 over 8, and then of course 16 over 8, which is 2. Now, in order to affect this, just like with the trapezoidal rule, we need our theorem, which states the approximation method. And it looks like this. The nth order Simpson approximation is b minus a, the length of the interval, divided by 3 times the number of subdivisions. And then we get an interesting play with the coefficients here. We have the first element of the partition, which is a, f of a, and of course the last element of the partition, f of b. That's like the trapezoidal rule. But here on in, it starts to vary. The coefficients after the 1 alternate 4, 2, 4, 2, and then n 2, 4, 1. That's why, again, we need the even number of subdivisions. So we have 4 times f of x1, the second element of the partition, plus 2 times f of x2, plus 4 times f of x3, etc. Again, last 3 terms, 2 times f of x sub n minus 2, plus 4 times f of x sub n minus 1, plus f of b. So I wrote up here in red an easy way to remember the coefficients, 1, 4, 2, 4, 2, 4, 2, 4, 1. So that's an easy way to think about remembering this. And now this problem really is very nice. Again, when you learn Calculus 2, you will study infinite series, and that's really the preferred way to give decimal approximations of transcendental functions. But this does, in this particular definition, admit to a very nice use of Simpson's rule. So now we can go ahead and substitute here. So b minus a is 2 minus 1. We have the 3, and n is equal to 8. And all we have to do is use our function, in this case, which is just 1 over x right here. So this is our f of x. And so what we all have to do here is just reciprocate the elements of the partition, remembering the coefficients. So we have 1, then we have 8 over 9 times the 4, then we have what? 8 over 10 times the 2, and then 8 over 11 times the 4, and then 8 over 12 times 2, and then here 8 over 13 times 4, and then 8 over 14 times 2, and then 8 over 15 times 4, and then the reciprocal of 2, which is 1/2. So what I did in the next line is just clean up the arithmetic a little bit. Of course, this is 1 over 24. Then we get 32 over 9. And when we look here, the 2 absorbs into the 10 with a 5. So we get 8 over 5, and then 32 over 11. And this is just 16 over 12, which is 4 over 3. And here we get a 32 over 13. And here, of course, the 2 absorbs into the 14, 8 over 7. And then we get a 32 over 15 plus a 1/2. This was much easier than the other problem we did with the trapezoidal rule that had all the powers in the cube roots. That was really, really a lot of busy work. And so now, again, I use my Google calculator again because it'll give you decimal place accuracy out to infinitum. And so upon this, we get 0.69315453 to secure the first 4 decimal places. And so, again, like I said before, the infinite series is usually the preferred method for doing these types of computations. But since we have this very special definition for the natural log, we can definitely use our Simpson's rule here. And what I've written here, fancy arithmetic. Everyone seems to think that calculus is this just mystical study. It's really basic arithmetic. But the elegance of the calculus is that so many great minds have developed this so that these numbers actually mean something. And we are done.